I gotta preface this. About 8 weeks ago or so, I said that I'm going to give the talk, and I was hoping I would be much farther than I actually am, and it turns out that I got hung up on implementing gems on the device. And I'm going to come back to that later. So I have some results with Kokkos, but I'm unfortunately not, like we haven't implemented our main kernels with Kokkos yet. So what's MRA? Unfortunately, I'm a computer scientist. I only know what I pick up in like a year or so. What I've been told is that it comes from signal processing, but it's being used in quantum chemistry. Madness is one of the implementations, and that's the code that we're trying to make fast using GPUs. It's being used for things like Hartree-Fock, Miller-Placid, density function theory, yada, yada, yada. If you know what that means, good for you. If you have questions about it, I'm happy to give you Robert's address. You can talk with him about that. What's important is that it guarantees, like you can go to a guaranteed numerical precision, basically by keeping on refining your function representation. So Madness, as I said, it's adaptive on a dyadic mesh. There's an example on the right side there of some molecule that they actually computed. Still a small one. We're targeting like hundreds or thousands of atoms. And you see there is a small example down there. It's basically, we end up with a tree representation that we go up and down or sideways depending on the operator that we're applying. It supports arbitrary dimensions. We most commonly 3D. There's teams in Europe that use 6 dimensions, so that's going to be an interesting target as well later on. There's 2 representations of these functions. The first thing we do is we project the functions into the scaling function basis, which is basically using Legendre polynomials. And depending on the accuracy that you're targeting, we're using 6, 8, or 10 coefficients. And in 3D, we end up with tensors of 6 cube, 8 cube, 10 cube. And we're building, through that refinement, we're building this ladder of subspaces. And that gives us the tree. We can, without loss of accuracy, transform that into a multi-wavelet basis, which is basically the difference between 2 levels. And that gives us tensors of 2K, so 12, 16, 20 cube. And that transformation down on the right there is a matrix multiplication. And that's what we're doing all the time, up and down the tree, matrix multiplications. So that's the bottleneck that we're facing, small matrix multiplications. The tree itself, in the scaling function representation, everything's at the bottom of the tree in the leaf nodes. In the wavelet coefficient representation, it's in the inner nodes, and the leaf nodes are empty. And we can we do this transformation to get from one representation to the other, right? So from the scaling function representation, we walk up the tree, we combine the child nodes into the wavelet coefficients and send them up. And eventually we end up with a representation where the leaf nodes are empty and the inner nodes contain the wavelet coefficients. And as I said, it's always 3 matrix multiplications per node just for that transformation. And when I say gem here and throughout the rest of the slides, for the transformation we're using, we're transposing A multiplied with B. So this is perfect for data flow, right? We're starting at the bottom and we're flowing something up the tree, and then whatever the result of that node, we can flow to the next operator and to the next operator and so on. So this is where I come in. We're trying to implement this with template task graphs. which is a model base that came out sort of out of the Parsec group, which is a C++ project where we represent the application in terms of an abstract task graph that can have cycles, and we're defining all the tasks that are in the system and all possible flows between the tasks. And then once we start executing, the data flows through these tasks, they get instantiated, and kind of unfolds into the usual DAG that we all know and love. And one of the nice things about this approach is that we can compose them, right? We have these edges, and we can take the Cholesky up there, and we can chain it with another operation, and all we have to do is flow data along an edge into the other. So we've done that for down there on the left. We get really nice depth first execution through the whole algorithm. So I'm going to skip that because I have a few more slides than I probably should have. For device tasks specifically, that's something that we've been adding over the last 2 or 3 years. We've been working on this. We made a decision to use coroutines in C++. Why? Because they're fast, and because they use only very little memory, right? If you want to suspend the coroutine, you don't have to move the stack away. You just save whatever local state you need. And we potentially have thousands of those tasks that are suspended, because at the bottom of the tree, there is a lot of tasks that have expressed their inputs but are not ready to execute on the device yet, so we have to stash them away, and once we can push them onto the device, we resume them. So it's it's memory efficient for us. So the way the task is structured is that it assembles its inputs and tells TTG what it needs on the device. It says, I need this buffer from this structure and this buffer from this structure, and then we'll go and look, well, do we have enough memory on the device? Where is that data? We support multiple GPUs, so we look. If all that data is on one GPU already, we use that GPU. If we have to move data, we'll move that data. And then eventually we'll come back. And you can submit the kernel. And the last step is to forward the result to the next task. So we usually suspend the kernel once or twice, at least. Sorry, not the kernel, the task. And we track the data provenance, so we know where the last modifications were, and we can move data around transparently. Once we're running out of memory, we will move data back to the host, evict it from the device, and bring it back once you need it. So all of that happens in the runtime system. You never have to deal with memory management. So that's all I wanted to say about TTG. Now, how do we map this to, or how do we map MRA on top of this? As I said, we do a lot of gems in that transformation. There are other operators that have way more gems inside the kernel, right? And this is only in one thread block. Function multiplication is 25 gems that are sequential in basically, that have to happen in order. In between those, we do things like tensor slicing, assembling larger tensors, scaling tensors, reduction. So using a batched API just doesn't cut it for us. It has to be in a larger kernel. And our gems are fairly small, right? Somewhere between 36 by 6 to 400 by 20. And then we need all combinations of transpose, so A transpose times B, B transpose, or A times B transpose, and so on. So it's a large space of possibilities. And the shape of these trees that you see on the top there changes between operators, right? An operator can add nodes on the top or remove nodes, can add nodes on the bottom, or remove nodes from the bottom, depending on what it does to the functions. What we did to extend the computational load so that it's actually worth offloading that into a kernel onto the device to keep all these SMs happy, is that we're batching nodes from many functions together. So we're forming the union of these trees on a node basis. So that gives us, and we're targeting about 1,000, maybe 10,000 functions that we're putting together. And that gives us about 10,000 gems that we do within a kernel. We're using Ampere to allocate memory on the host, so pinned memory on demand, so that when the runtime system decides that it has to evict data, it will evict it into pinned memory. But we don't want to keep that pinned memory around. We will give it back to Ampere once we're done with that, to keep the amount of pinned memory that we have to allocate as small as possible. And we have it's a little embarrassing, to be honest, but I wrote some small abstractions just to get things going before trying to dive into Kokkos, which basically supports the zero execution CUDA and HIP. And that works well. So we have, I would say, 60% of the operators that we need, and I have a student right now that's working on convolution, which is probably the most complex operator that we'll face. So the goal would be to replace that custom code down there with Kokkos. That would be nice if we could make that work. Takeaway here is, it's really sad, right? We have to deal with all the gems that we're facing. A typical kernel, this is the compressed kernel, so when we walk up the tree to go from the scaling function basis into wavelet basis, we take the 8 input tensors from the children, put them into a larger tensor, so that's slicing. Then we apply the transform, which is those 3 gems, and then we do some more slicing down there to extract the top left slice and set it to 0. And in our abstraction here, those assignments to the slice is parallelized over the team internally. We can't do that with Kokkos because we can't drag the team into that assignment operator, so we have to change the way we express these kernels if we use Kokkos. And that is actually the hardest part. I have to convince my boss, who only cares about a nice abstraction, that this is a good thing, right? That we can't just write an assignment. We have to have the team pass into a function. So that brings me to the thread block level gems, and this is where I spend my time for the last couple of weeks. We need to get as much performance out of those. We know that those are the bottlenecks. I started with Cutlass, and there was brain matter everywhere because it's just a mess, right? Mark said that it's not for mortals. Turns out I'm a mortal, so yeah. I gave up on it. Someone pointed me at Kublas DX, which is somewhat more sane wrapper around Cutlass. You still have to do manual pipelining, right? It doesn't, you have to move things from the global memory into shared memory, apply the gem, move it back out, and so on. And everything is a compile time constant. The size is a compile time constant, the leading dimensions, basically everything. So we have to pre-generate all of these gem operators, and compiling that takes forever, but it works. There's still some guesswork involved, right? How big is a stage, a pipeline stage? Or should we stage it back through? Should we stage C back through shared memory? The docs are not really clear on that, but we get really nice performance. So we get a 10x speed up over the host version of Madness. for anything that's not just a single function. And you see here, starting at about 250 functions and then 450 or 500 functions, we're running out of memory on that A100. It's only 40 gigabyte, so we're starting to evict. That's why those red lines start going up again. So we need to improve our eviction strategy. Right now, we only start to evict once we really don't have any memory anymore. So we should keep like a window of memory available so that we can overlap the eviction with actual computation. So that's the nice part. The performance of the gems, the gray line here, that's what I wrote manually, right? 3 loops gives me about 350 gigaflop per second. With Ku+Dx, I get about 2.5 teraflop. That's really nice. But then you look at the specs, and it says, well, you should get 20. Then we look at n-side compute, and it says, you're doing a lot of shared memory bank conflicts. And that's a very sad panda. Why do I do this, right? Why do I use Ku+Dx? And it doesn't work. It doesn't give me peak performance. I don't know. We'll see. That's something. So now I come to Kokkos. The good news is that using Kokkos in this benchmark gives us the same performance. So that was an important step for us to verify that replacing that custom code that we have with Kokkos and then dealing with things like the limited shared memory that Kokkos allows for doesn't degrade the performance. So now we can move on and port some of our kernels to actually using Kokkos. The value proposition of Kokkos for us, portability, of course. We need to rethink our code structure, and that takes some social engineering on my side. The biggest thing that I really would like to have is performant, portable matrix multiplication kernels in Kokkos. Because I don't want to deal with this, right? I have a lot of work over here that I need to deal with. I wish someone would just give me something that is really portable across all the systems. We'll see. So that's it. I think we're making progress. It's been about a year now that we've been working on this code, and we're getting close to having something actually realistic to run. And then, yeah, the quest for team-level performant gem is still ongoing. That's all. Thank you.
Thank you. So I have a bad news and a good news. The bad news is we have very little time, so we only have time for one question. The good news is we have a bonus presentation just after this one. So, do we have a question? Yep.
I'm going to get up and talk anyway. So with TTG, can you place it kind of in the tasking like landscape with Legion and HPX and Uinta and so forth?
Yeah, so that is a good question. So I like to think of it as like a forward-looking task discovery, right? A task will send something to the next task. That's how we discover them. So that's the opposite of, say, StarPU. We don't deal with region or like memory structures like Legion does. And I know that there's a code written in HPX that is sort of similar, like it's working on octrees, and I want to know how that works with HPX, and then I can tell you more.
Thank you. Thanks again.